right, so we finished up our last module and we are moving on, but remember we always take what we know, apply it to what we don't know, and this is kind of the last part of our atomic level of science. The next couple of modules we're going to move into involve like some earth science, rocks, minerals, things like that. So we're going to shift gears after these next 2 weeks. We'll finish up. You guys will have spring break, and then we'll kind of hit a whole new subject matter after that, okay? So we just left light. We learned a whole bunch of information about light. We learned that light was really packets of photons that move along. So every time we think we learned something, we end up with another question, another little part of it, and that's science, right? Science is science is just questioning what has happened and then coming up with a hypothesis and coming up with a theory, and until someone else proves it otherwise. But is it ever actually truth? It is until someone proves it that it's not true, right? So science is all about questioning. And so we just keep taking these little parts and saying, hey, how does this relate here and how does this relate here? I hope that what you've seen is as we've moved through all of these different concepts, whether it's through atoms and energy or gravitation or now light, and then as we move into electricity and magnetism, that you see that there's a constant, there's consistency in there, and that's because the creator of the universe, who has order, is the one that put it all into place. So it makes sense that there's some consistency across the board with that. Okay, so as we move for module 11 into electromagnetism, so typically in the science world, it is abbreviated as E&M. You can take whole college classes just on E&M. It's a sub-level of physics. And that's because, who did you get to read about? What were you guys reading about? Who was the guy? Do you remember his name? Maxwell? Okay, so the father of physics, he's kind of known as the father of modern day physics. And so a lot of this, we are just hitting the milk skim surface area, you know, when you heat up milk and it makes that little real thin film on it. So we're hitting that. If you choose to go into something deeper in college, you'll get to explore all the other parts of it. But what's interesting is that today we're going to take what you read, and I'm going to take some end of the chapter that you haven't read yet because they tie together. And so when you read that, you'll say, oh, we've already done that. I know what that looks like. So we're going to look at both electricity and magnetism today. And then next week, we're going to deal with circuits. And we've got lots of fun circuit things. That way we can have plenty of time for the labs for that. So for electricity, it says electricity and magnetism. I wrote them up here. We've got electricity, we've got magnetism. They are different ends of the exact same force, okay? So when we talk about it, we learned last week that we've got the electromagnetic force, and it's actually tied together, right? We've got one that's working in a wave, maybe parallel, vertical here, and we have one that's working horizontal, and they're working together. And so it is very difficult to separate and say, this is just electricity, and this is just magnetism. Because remember when we were doing the water stream, and we were talking about it being ionic, and how we could bend that stream towards us? Because at the very core of everything that we have atoms that are made up of negative electrons and positive protons. So at the very core of everything that we have created and all of matter are both negative and positive fields. And so we have that push-pull that moves electrons along. Electricity is actually the term for moving electrons. That's why you see electron, kind of like the first part of electron in it. So the whole definition of electricity means electrons are moving. So if we've got moving electrons, that means we have a moving negative charge. When we have magnetism, we're dealing with those positive and negative charges. When we looked at light, we had the electromagnetic field where we've got two separate fields, and it didn't need matter. Why didn't it need matter? Because it had that push-pull that's moving it along. Kind of like the little scooters if you go to the skate rink and you just, shake it, it makes you go forward. So just by the push-pull of what we've got, we can cause motion with that, okay? So as we have learned with all of our forces, gravity force, everything, if you have a stronger charge, you're going to have a stronger force, right? They're going to be directly related to each other. And then we've also learned that there were some opposites. We called this inverse, right? We learned about inverses when we were looking at work and the forces of work when we were dealing with levers. So if we made something longer as we pushed on a lever, then it gave us like twice as much force on the other end. So we're dealing with the exact same process. We're just looking at it on an atomic level. Now, so the force that is applied between something depends on the distance that they are together. If I have a charge on one and I have a charge on another and they both have attractive forces, the closer they get together, the more that force is going to be. And it is specifically a squared version. Okay? We've seen squared as we were looking at the acceleration with gravity, with some forces there with our gravitational pull. For the universal law of gravitation, it says that any sort of matter has gravity, right? No matter what you have. So this eraser has its own gravity, gravitational pull. I have my own gravitational pull. Any of those Jolly Ranchers have their own gravitational pull. It's not very strong because you need more matter to have more pull, but everything has some sort of pull, and that ties into the fact that at the atomic level, all of these have some sort of charge. It's either going to be neutral, it's going to be positive, or it's going to be negative on it, okay? So we have three different principles that govern our electromagnetic force, which you'll notice are very similar to the gravitational forces, that all charges attract or repel one another, right? No matter what you have. So a positive is going to attract or repel with the negative. Okay, so like charges repel, while opposite charges attract. Does this look like anything that you would know from a magnet? Yeah. So when we are talking about electricity and we're talking about magnetism, the rules are the same. So for charges with electricity, like charges repel each other and opposite charges attract. The rules for magnetism, like charges repel each other, opposite charges attract each other, okay? Remember, they're the same force, so the rules are going to be the same with it. We know that the force between them is directly proportional to the amount of charge on an object. So if I charge this object up a lot, with a greater force, a greater charge, then the combined force between them is going to be greater. And it's a direct relationship. So if I double the charge, I have double the force on it. If I half the charge, I have half the force on it. And then the force between two charged objects is inversely proportional. So that's where we're here. We've got an inverse. Inverse means, like mathematically, you're going from the top to the bottom. So when one increases, the other decreases for it. So those are our inverse forces there. There we go. I am going to play this little video, hopefully.
things happen. Is it magic? No, it's not magic. It's static electricity. Before understanding static electricity, we first need to understand the basics of matter. All matter is made up of atoms. Inside an atom are protons, electrons, and neutrons. The protons are positively charged, the electrons are negatively charged, and the neutrons are neutral. Therefore, all things are made up of charges. Opposite charges attract each other, and same charges repel each other. When you rub balloon with your hair, loosely bound electrons loses their place and stick to the balloon. Now balloon has more electrons than neutrons, and it is negatively charged. And as the balloon come near your hair, balloon will attract your hair towards it, because of the rule that opposites attract.
All right. Let's see, what's that? All right. Okay, so that sounds like I learned that in 3rd grade, right? Okay, the thing that is great that we can tie into it is that we have learned that matter is neither created nor destroyed, right? It's simply moving, and that's what we've been learning about energy, and as we were learning about light, that it's either moving from one place to another, it's been in one place and it's transformed into a different form, but it's not actually created. So as they were talking, for example, I've got positives and negatives, or negatives because they're red, and positives for the green of Jolly Ranchers. If these negative electrons here go somewhere else, they haven't gone away. They're simply hanging out over here. So if you move 2 of your colors over, you can do that. So now that you have maybe 4 and then you've got some that are combined, do you still have negative with your negative ones? Yeah, they're still all negative. But now we have negative on the other side also, right? And so now we have changed, instead of having positives, like only positives, only negatives, now we have 2 different things that have changed, okay? And so we've got something that wasn't negative and now is negative. And so it's going the way that maybe something that Nathan has with his charge is going to react with this new set completely differently than it had if those charges weren't already there with them. And so that's the same thing. We were learning that in light. And so to tie that in, we learned with light that light is really a photon, right? A little packet of energy that is moving along, and that as photons can actually change levels like the electrons, they can be transferred, and that produces our energy. And when there's extras of them, we see light for it. And so I kind of have it here. We have all these photons. We know we've got this electromagnetic wave. I didn't draw it where it's both of them. We just have it moving. As it starts moving, these are rubbing along each other. And we know it's producing heat, correct? Heat tends to separate things. If we go back to what we were learning about solids, liquids, and gases, how do we transform from those different stages? Heat, right? If you want something to go from solid to liquid, you're going to heat it up and melt it. And if you heat it up enough, it's going to turn into a gas. And so we've got this heat. The heat causes them to react differently, so they're actually spreading around. And sometimes there's not as many that are needed, and it releases these extra ones. And that is what we see in light. Not all of them are released in the wavelength we see of light, but some of them are released in the wavelength that we see of light. So it's kind of how it all works together. We're taking all the different individual parts, we're tying it into one big thing and saying, oh, this is how it works, okay? So We can also say that we know electrons and protons and neutrons are governed by these forces of positive and negative and what they pull on each other. So because photons are little packets of all of it together, we can also say that photons can have either an attractive force or a repulsive force, right? So the more charge that something has for that little photon packet, like the more charge, then the more that it can exchange. So we've just broadened our view. We've taken it from like individual electrons to now we're saying the same thing works if we have an entire packet that's a photon packet, right? And so if it's going to be the same for our force and our distance, isn't it going to be the same for photons? That the exchange of the photons is inversely proportional to the square of the distance between them. So we get to take what we've done on the microscopic level and we get to apply it to a bigger level. And that's actually, as you start taking like ACT tests or bigger tests like that, that's called inductive reasoning. Okay? Inductive reasoning means taking something that you know and you're applying it to a broader scope. Deductive reasoning is taking a whole bunch of broad things and you're making maybe one decision out of it. Okay? So as we look at how all of these things are moving around, we've got electric fields, right? The whole area that something affects around it is your electric field. And static electricity that we were just watching and the charging objects is a buildup of the charges on the surface of a material, okay? And so it's going to affect the whole area around it. And every table gets a balloon. Okay, so how do we take this movement? How do we know matter's not created nor destroyed, we can't get rid of the atoms, how do we move them around so then they can change differently? Okay, so we have balloons. I'm going to use you guys as an example. And our balloon has a certain charge on it. It's either going to be positive or negative. If it has a little bit of static, it might, see it's kind of like attracted to my shirt a little bit. You know, different materials transfer electrons easier than others. We've learned that, we'll look at that when we talk about magnetism too. There are certain materials that are more magnetic than others just because they lose electrons easier. So if I were to rub this in my hair, my ponytail here, back and forth, we learned about friction, right? Friction is one surface against another surface. So rubbing this is friction. Hopefully, are we sticking out? Yeah, okay. So now what has happened, and this is where I have your little balloon thing, your little Jolly Ranchers too. If we are looking at friction, friction is rubbing one surface against the next. Okay? So when we rub one surface against the next, more go one direction and more go the other direction. And we end up with opposite charges. So friction will always give us a positive and a negative. We are transferring from one to the next when we are changing with friction. And so then what do we know if we had a magnet in a North Pole and a South Pole? What do we know about that? Opposite charges attract and like charges repel. So I have now transferred, because of friction, electrons from my hair to the balloon. So what charge does the balloon have?
Negative.
Negative. What charge does my hair have?
Positive.
Positive. So they're attracted together. Okay. I want you guys to all charge your balloons. Okay. And then turn around and hold your balloon next to each other. So here, you guys take your balloon and you're going to charge your balloon, and then you are going to pair up with Andrew and Dennis. You can pair up with the girls.
Oh no, you got a ponytail.
Okay, hold it by your string. Gotta hold it by your string. Okay. Have them come near and see what they do. What can you deduce about your jacket?
It's very staticky.
What charge would it have?
Positive.
Positive. Okay, so what's happening to your balloons?
They don't want to go together.
They don't want to go together because, like Nathan put a negative charge. Are you, okay, what's happened to your balloon? Oh, it's, they're not going to each other and they are going to you instead, right? Because your body has transferred some of the electrons onto the balloon, so you have a more positive charge. So does that make sense that the balloon's attracted to you? Yeah, the balloon is more attracted to you. But when you try to put them together, we're seeing that repulsion because you've got a balloon that's negative, another balloon that's negative, and they're not wanting to go together. So that is our friction. Now, conduction, I like to say, is like a little train conductor, right? There we go. Conduction is simply going from one to the next. So we are going from where we were to the train was on the left and now the train's on the right, and it's the same train. Right? So as the train moves down the tracks, does the train ever change? No. So conduction means that we take whatever charge and it just goes along for the ride. So when we are conducting for our transfer, it says that we are charging it by allowing it to come in contact with something that's already that. So if our train is already full of a bunch of negative, like full of electrons, so it has a negative charge, and you open the path and you let it go down, now it's got negative all the way through. So we're taking the same charge and we're applying it across the line. So if we started with positive, our new item is going to be positive. If we start with negative, the new item is going to be negative. Okay? Do we see how that's different from friction? Friction, we have the same amount. Friction, we're moving pieces around. I'm rubbing together, so you're getting a little bit like me. If I had a chalkboard and I rubbed my hand, or even this because it's dirty, rubbed my hand, what's going to happen? It's going to look black. Some stuff from the board is now on me. So that's our friction. We're changing places. Conduction, we're just sharing the love all the way through. Okay? Now, induction, okay, and this is where I want you to use your, get 3 and 3 and put them in the middle. Just get 3 of each of your colors and mix them up. Okay, so now you have your little packet, your item in the middle, and what charge does that packet have? Neutral. Why? Nailed it. We have an equal amount of positive and negative, so we're neutral, right? So if I bring a negative charge, so you can just choose one of your colors, if you bring a charge towards it, what do we know? We know that like charges repel and opposite charges attract. So if I were to bring this near my little item, and I've got a red one, what are all the red Jolly Ranchers going to want to do? Go away, because they're the same. And he's got green, what are all the green ones going to want to do? Get close. So for yours, if you have your little mix, and I've got bring blue ones, all of the blue ones want to do what? Go away. They want to move as far away from it as possible, and then all the green ones are going to want to get as close to it as possible, but they have to stay as a unit. Does that make sense? So how is your little packet rearranged? What are you pulling? Okay, so if I bring a blue charge, what are all the blue charges going to want to do? Move away from it, and all the red charges are going to want to come close. So now they have rearranged themselves. right? Is this your packet? So if we bring red ones, your red one's gonna go there, and they still have to stay together. But so now, in all of your new little packets that you had, you still have six. You still have 6 Jolly Ranchers, right? They still have to stay together, but are they all mixed up like they were before? No, they are arranged differently. So we still have the same amount. They're still in the same place. They've just changed locations of where they're at. So bringing something near has now caused your little packet to have a pole, right? It has one side that's positive and one side that's negative. We learned that when we were looking at ionic bonds, right? And if something was, the water is like, it's positive on one side and it's negative on the other side. So we still have the same amount of our charges. They're just, instead of being mixed up and neutral, are they still neutral? It's neutral if it's all by itself, right? But if I bring something near to it, that is that opposite charge, it is going to want to connect. We're going to have that. And that is where you get those shocks. Like late at night, if you have one of those fuzzy blankets, you know, you turn over and it's like, you can see all the shocks for it. So that is our induction. It is temporary because it only happens because something has forced it. Because otherwise, it's just going to be a whole mix together. But when you bring that charge together, it's like, maybe it's kind of like your siblings in the car. You're like, not sitting by him. You know, and you might change seats. So you're still all in the car. You're just in a different seat to not be by them. Right, so you've temporarily rearranged yourselves, but what it has created is it has created a gap to where now energy wants to move from the positive to the negative, or from the negative to the positive. And as it gets closer and closer, the air between that gets charged and it can actually jump. So when we see that spark, that we are actually seeing the release of photons as our energy transfers from the positive to the negative side on it. So that's why we get that. Okay? Now, objects can be charged permanently by induction. Induction usually, does anyone have an induction oven? Like induction stovetop? They use the special, so they're never hot. They're never hot. You can touch them. They have special pans that you put on them. So objects can be charged permanently by induction by, it says bringing it near a neutral object and then grounding the neutral object, okay? So we can take something maybe like iron, like a nail or whatever, and you wonder like, how do they make magnets? This is how they make magnets. When you have an item that's all mixed up, okay? We're going to go over and look at the magnets for this. When you have something that is all mixed up, you can bring a force, typically electricity, near it and make it rearrange just like we did on a small scale, right? What does it say? It says that's a temporary rearrangement. However, if you do this long enough, this rearrangement becomes permanent. It becomes a permanent rearrangement. With enough force and long enough time, you can permanently change where those are at a day. Okay? Let's see. Okay. So to tie that in with magnetism, okay? Same things. All of our magnetic forces are because of movement of these charged particles. Same thing back and forth. And so just like we were looking at positive and negatives lining up, when we are arranging, in your book it had like little blue and red things, when we are arranging, and each one of these has a field, when they start to all line up, we get greater forces, and we get a magnetic force, okay? And it says because they contain a magnetic domain. So what does that look like? When we have our forces, each part of it, because we have all of our electrons, you know, moving all around, and changing and going back and forth, releasing some. You know, we've got all this movement where we end up with, you know, positive ions and we end up with some negative ions. We can make those line up. Like I said, with that induction, we can make them line up where we always have negatives in one area and we always have positives in another area. And most everything has a magnetic domain around it, kind of like gravitation. But the more that you get them lined up, the more magnetic something is. So there are certain metals, like iron, that are super magnet, like have magnetic properties, but then like aluminum, you can't stick a magnet to an aluminum. Anything that's aluminum will stick for that, okay? And that is because as that magnet draws close to it, has anyone been able to stick a magnet to drywall? No. Because the pull of that magnet can't rearrange the particles in our drywall here to make all of their magnetic domains actually line up. So there's particles you're like, I'm never going to be able to rearrange that. Some that we can rearrange it, okay? So magnets, exact same thing. I want everyone to get up. We're going to go to the magnet that's over here. Magnets have two sides because just like our energy, they are both positive and negative. We're going to finish this and then we're going to do our lab for today, which is great. Okay? Jonas. Here. Okay. So we have a magnet. Magnets have two poles, north and south. If I cut this magnet in half, will I have one side that's north and one side that's south? What do you think? No. The answer is no. Because this is called dipole. A monopole, mono meaning one, di meaning two, monopole does not exist. Scientists have tried for years and years and years and centuries to find it. If they ever could find it, it would completely change science. But dipoles are what exists. So if I were to break this in half, I would have two complete magnets. One side would be the north or the positive side, one side would be the negative side, and it would rearrange it because within this magnet, we have rearranged the particles. So it makes sense because I have enough positive over here that are pushing or that are trying to connect with my negative. If they were all positive, they'd all try to go away from each other, right? Because isn't that the rule? Positive repels positive, negative repels negative, and so then would it even get to stay together? Technically not. On an atomic level, it'd all be trying to go apart from each other. So, who wants to use, oh look, did it already move the magnet? Okay. So, this is where we're looking at the magnetic fields. I'm pretty far away from that magnet, and it's pulling it, okay? What happens if I come down closer to it? So that was pretty slow. Okay, did we see how that went faster? So that is the relationship of the distance gives you our inverse relationship of the distance squared. So as I come closer, I have a much greater force. I'm going to turn this and see if I can get the positive. See, the positives don't want to go together like that. Okay? So we're going to take those and we're going to pull that one off in just a minute. So as I get closer, there's a much greater force versus if I'm out here, we saw that it already turned towards it, but it wasn't actually drawing it in, correct? Okay. So let's look at these. What's this? Let's get him really full. So we can actually see the field. Do you see the field on that? How are all of those iron shapings? They're in the shape of would you say a sphere? Circle going around it? Okay, so if I put my north to the north, what do we know? It's going to repel. So let's see what happens to all of our iron. filings. So we're getting to see the invisible. We're getting to see them react to it being repelled, okay? If I pull up, and so as we got closer, they reacted more, right? What if we did it this way? So technically, between this south and the north, there should be forces that want to draw it together, right? Let's see what they do. See them all stand up? So as we pull away, it shrinks back down. As we pull it back in, we stand up, and it will even transfer them across the board. Okay, so this is neat. If we have time afterwards, you can come play with the magnets where you can actually see. We're getting to see what we can't see, right? Because you've got these iron filings in the middle that are reacting to the forces, those unseen forces of the magnets and pushing them away. Okay, let's see if we can get a force field here. I've been able to do it a couple times. Okay, when we have force fields, what do we know about our south end here? It should want to draw things to it, right? And our north end should want to draw things to it. But what about things in the middle? Maybe they don't know which way to go. Okay. Come look close, and what do you see? What shape is being made in the filings? Can you see it? You see what the filings are doing on the south side? Anyone see? Do you see the arcs? So we have these, this is making a circle right there. Making a circle, let's see if we can get it in. Look at this part right here. Do you see those lines? How they go out like a sun ray from the south? You guys see that? Okay. And then look at this here. Right about here, you can see where it looks like this is one circle and this is one circle. These turn in and then it starts kind of changing again. Right there, we're getting that circular movement along here. So this is the actual magnetic field that we're seeing. Okay, look how much deeper it's getting. We see those now? So it's pulling. So our magnetic filings are allowing us to see the unseen. So we don't get to see that magnetic field. We don't get to see what it's doing, except now we can see that every part of, you could say the air or all the pull or the forces there is pulling towards this south end all the way around. So we're getting that circular movement, but we're also getting that same circular movement here around the north end. And look at how the filings have built up around the edges. But has there been a lot of buildup in the middle? No. We haven't had a lot of buildup in the middle because we have these two opposing force fields, and so there's not a lot of room for those spaces. It's going to want to go to one side or another. So that's a good example for that. So we're going to get to move on to our other lab and get to see how, as we are transferring by friction, induction, or conduction, you'll have to decide what you're using. How are we moving the charges around? We're going to get to see what happens to some pieces of aluminum.
So we're on experiment 11.2, page 592. Go ahead and bring the books over.